Hello. We'll study how to apply the finite difference methods for solving ordinary differential equation boundary value problems. The idea is that we approximate derivatives in ODE with selected finite difference formulas at every point. And the points may be excluded. Yes, it depends on the boundary conditions. The discretization of the ODE results in a system of equations. If the differential equation is linear, we will have a system of linear equations. If the differential equation is nonlinear, we will obtain a system of nonlinear equations. Okay, in chapter 8, we studied how to derive finite difference formulas for various derivatives like first derivative, second, third, and so on. Here are a short list of the difference formulas. And in today's lecture, I will show you how to discretize an ODE with its boundary conditions. I hope you will master the procedure. Okay, the first example. We'll solve such a boundary value problem. Yes, with the boundary conditions. We will use only 4 subintervals. This normally we'll use way more subintervals and points. Not just this. Say 4 subintervals. Okay, this is just a demonstration. Okay, so here, and the boundary, the two endpoints is 0 and 4. So we use 4 subintervals. So the size, step size h is 1. And the boundary conditions, yes, this is like solving initial value problems. Okay, we want to find, say, hey, at y0, what's y, when x0, what's y's value, when x is 1, x is 2, and x is 3, right? And 4. But here, with this condition, with our given boundary conditions, and the two values are given, so of course we don't need to find them, they are given. So our purpose is to find the values for y at x is 1, y at x is 2, x is 3, yes. Okay, so we'll see how to do it. There are many different formulas for here, the second derivative. Here we only have a second derivative in our equation. So there are many choices. And when we choose, we select a formula. Which formula? Yes, which one? When we select the formula, we will have some standards to follow. So of course, we wish a formula could be valid to many points if it's not all. Each point here, if it's not for each point of our interest, it should cover more. Here we only have 3 points. Okay, you check it. We just now look at this table. We'll see which one we will like. We want first a formula could be applied to as more points as possible, if it's not all, for all points. Secondly, we want the truncation error to be smaller, Okay, so which one is, oh, this is small, this is smaller. We have a much smaller truncation error with the 5-point central difference formula. However, we will see how many points, how many points this formula is valid. Okay, you check now. You check at those points. 1, 2, 3. How about when x is 1? No, you have a minus 2 there, a minus 2. We don't have that point, we have I plus 2. I plus 2 is fine, but we don't have a I minus 2. So this formula is only valid for this point, x is 2. Okay, same reason. Oh, this formula is only good for 1 when I is 1. And this formula is only good for I when x is 3. Oh, I is which one? 3. Okay, so we'll not consider this. How about this one? It only works. This one it only works for I plus 2. Say this point for 2 points. Okay, but the truncation error. Oh, that's a problem. Okay, so when I choose it, it has the largest truncation error. Okay, so when I use this, and this one is only valid. How about that formula? That formula is only valid for its backward for 2. Yes, for this point and this point. It's not valid for 1. So, and the truncation error is also a problem. So when I use this, okay, this one, only this one, it's good. It's the 3-point central formula. It is valid for all the points in which we're interested. Okay, so, and the truncation error is small. So, we choose that formula. Okay, the 3-point central difference formula. We use that to replace y dot prime. Okay, it's y I minus 1 at I. Okay, when x is, well, xi at, or x is xi. Okay, we have formula which one? This minus 2y sub I plus y sub I plus 1 over h squared. That's the second derivative. Okay, and y, that's just yi. Our value is xi, yi, right? Yes, you may say, hey, this point is at xi, yi. Okay, so xi minus 4. Okay, I is 1, 2, 3. Okay, so we have this. When I feel happy with this, we'll simplify it. Each side multiplied by h squared. So we will have h squared. So we'll not have this denominator. Now, yi minus 1, yi was I plus 1, they're unknowns, and we'll put all unknown terms on the left hand side, so combine like terms. Okay, it's y sub I minus 1 minus 2 plus h squared y sub I, and plus y I plus 1. Okay, and the right hand side will be xi x sub I minus 4 h squared. So this I changes from 1, the text value 1, 2, 3. Okay, now we'll see. H is 1, right? In our case, when we use M is 4, M is 1, H is 1. So in this case, this is y sub I minus 1 minus 3yi plus yi plus 1. And h is 1, so xi x sub I minus 4. Yes, I changes from 1, 2, 3. Okay, now we can simplify it. That's it. And we'll see. When I is 1, we'll try to make it useful. Okay, and so that we can solve, we'll set up a system of equations so that we hopefully can solve it. Okay, when I is 1, you see y I minus 1 is 0. Y at 0, what's the value here? Y of 0 is 0. Y of 4 is also 0. Okay, so we'll use this left end, the condition, boundary condition at the left end point. That condition is called conditions. The conditions here are called Dirichlet boundary conditions, and it's 0. That's okay. Minus 3y1 plus y2 is x is 1. x1 is 1 here. That's x1, x2, x3. Okay. x1 is 1, so 1 times 1 minus 4, that's negative 3. Yes, we have this. And y0 is 0, so the left end, we just keep all unknowns terms on the left side. Okay, I is 2 now. When I is 2, we'll see as y1 minus 3y2 plus y sub 3 is x sub 2 is 2. 2 times 2 minus 4, which is negative 4. Okay, now finally I is 3. When I is 3, you have y2 minus 3y3 plus y sub 4. Remember, that's y sub 4 is the right end point, right? The condition is given is 0. This is 0. We applied the boundary condition. That's just what here. Y x4, x3 is 3. x3 minus 4. That's negative 3. Yes. And eventually we arrive at such a system. It's a linear, yes, such a linear system of 3 equations in 3 unknowns, and we can solve it for x, for y1, y2, y3. Okay, therefore you get the value here. You get the y1, y2, y3. Okay, we get the value here. And for such a boundary condition, we can find the exact solution. The exact solution will be what? The exact solution is analytic solution is this, such a function. Okay, and we evaluate it at x is 1, 2, 3. You get those values. So there are exact solutions. And not so close, quite close, but not so. Okay, this the same, this the same. Okay, here is the graph. The green curve is for the exact solution. You see, so the boundary conditions, of course, they are exactly on the curve. They are on the curve. And y1, y2, y3, they are close to the curve, but they are not on the curve exactly. So as this, and the problem is you may say, oh my, there is a solution is better than nothing, right? But it's not so good, you say. And why? If we want to know the reason, that's because h is large, is 1. As I said, our purpose is to demonstrate, to show you how to discretize the problem. Okay, so how about you choose smaller h, use more subintervals. That means, okay, how about using 10 subintervals? Now you see that on the graph, our eyes cannot tell the difference. Sounds like it's exact solution. I mean, all the approximation points, the numerical solutions, they seem to be on the curve. Oh, yes, exactly. And so, not. If you show more decimal points, okay, they are not. That's just very close, but not exactly the same. The numerical approximation are not exactly the real solution, and we can use 100 points or more points. Okay, and you'll get a better solution. Okay, hopefully now you can tell how we discretize the problem. Okay, that's our fourth example. Now, second example. Wow, this time is such a boundary differential equation with such boundary conditions. And well, P, Q, R are functions of X not given, alpha, beta not given, AB not given. How could we do it? Again, this is just to show you how to discretize the problem. Okay, now given that we will have n subintervals, we have those points equally spaced. Okay, x0 is the left endpoint, x sub m is b is the right endpoint. We have x1, 1, 2, 3. Those points. Okay, and the boundary conditions are still Dirichlet boundary conditions, so we don't need to find the y value at the two endpoints because they're given. So we focus on the interior points. Okay. Okay, at the xi, yi, we'll see what will we do. We mean those points. Okay, those points xi, yi. Okay. Here we have second derivative and fourth derivative. We'll choose formulas here like this. Now we're supposed to apply this. Both have a big O of h as their truncation arrow. Yes, could we choose the formulas differently? Say here, I choose this. I choose a forward or backward formula with big O of h. Could we do that? Of course, no problem. You can do it. But the problem is, if when we choose formulas like this here, if we have pool, this you have a smaller truncation arrow. This have a larger one, so therefore it's this one, the poor one, the one with larger truncation arrow, which dominates or which determines the truncation arrow overall. Okay, so just be careful. Normally we should choose formulas with the same truncation arrow. I mean in big O notation. Okay, so that's an issue. And for the convenience of writing for me in such a limited space, I don't want to write each time things like this. That's horrible. We just use p sub I, q sub I, r sub I to denote p of x sub I and so on. Okay, so that's a shortcut in our case. Now we'll see how to derive it, how to discretize the problem. First, the left endpoint, the left hand side as y sub I plus 1. I prefer to rewrite it in another way. Okay, it's fine. Plus 1 minus 2yi plus y sub I minus 1 over h squared. And pi, this is p sub I, y prime is this, yi plus 1 minus yi minus 1 2h. And now this term, q sub I, yi plus r sub I, finally is this last term. Okay, again, we'll simplify it and combine like terms. Oh, yes, and we don't like denominators. Each side times 2h squared. Okay, we'll see. You have a 2, 4, 2. Okay. And this, we will have h. Right? And this we have 2h squared. This we have 2h squared. Okay, let me copy paste it again. Okay, so this is 2y sub I plus 1 minus 4yi 2yi minus 1 is pih yi plus 1 minus pih yi minus 1 plus 2 qih squared yi plus 2h squared ri. Okay, combine like terms. I plus we'll make it order. This first, then this, then this. Okay, we change the order. I minus 1. We have sub I minus 1 this. Okay, we have a 2 plus p sub I h y sub I minus 1. Okay. And now this is gone. And now y sub I. So we have minus 4 plus 2 q sub I h squared yi. Know these two terms. They are processed. Okay. Now y plus 1. We have these two terms. That's 2 minus p sub I h yi plus 1. Okay, that processed. We have this left. So 2h squared r sub I. Yes, now we will. That's the formula. Okay. For which one? I is 1, 2 until n minus 1. Yes. Let's see how to apply the conditions. Okay, how to set up a system. In this case, it's a linear system because this equation is a linear equation. Okay, it's a linear differential equation. Okay, so let's see. When I is 1, let's see what's this. That's what? As y sub 0, it's given its alpha. In that case, we move it to the other side. That's negative 4 plus 2q1 h squared y1. Okay, that second term. And third term is 2 minus p1h y sub 2. Move, that's 2h squared r1. And this term, we move it to the other side. That's minus 2 plus p1h. It's alpha. Y of 0 is alpha. Okay, not y of 0, y of a. That's x sub 0. Okay, now I is 2, 3 until n minus 2. Okay, we'll see what's that. You just copy paste this equation to this place. Copy paste. Okay. And now I is n minus 1. We'll have 2 plus p n minus 1 h y n minus 2, right? This. And this term 4 plus 2 q n minus 1 h squared y sub m. This term, what's this term? It's y of y sub m. Well, that's the right endpoint. The condition could be applied at yes, at the right endpoint. That condition. boundary condition, okay, can be applied. So therefore this term will be a constant. Such a term will be a constant. It's 2 minus p m minus 1 h. That's ym. Ym sub m is beta. So it's constant. We move it to the right hand. So therefore it's 2h squared r m minus 1 minus 2 minus p sub m minus 1 h beta. Yes, we have this term. So at the first point, the last point here, in our case, we apply the boundary value conditions. So therefore, we'll set up a system with the boundary conditions with a coefficient matrix like this. Okay, like this. We have a, y is b, y will be y is y1, y2, ym minus 1 transpose. Okay, it's a column vector. And we'll see how about a. Yes, we have this. We set up, oh, it's negative 4 plus 2q1h squared. That's y1, y2 is 2 minus p1h, and others will be 0. They are 0. Oh, and I is 2, we have, when I is 2, we'll see what's this. When I is 2, you have 2 plus p2h. And negative 4 plus 2q2h squared. And we have 2 minus p sub 2h, all zeros. Okay, followed by zeros. Okay, and 2 plus p3h, negative 4 plus 2q3h squared. And 2 minus p3h, and followed by zeros. Okay, and this way you set up, and eventually is this you set up there, and that's 4. That's given that that's the nth column. You have 4. What? You have 4 plus 2qm minus 1 h squared. Before it is 2 plus, yes, pm minus 1h. Anyway, it's ugly here. Oh, I'm sorry, we don't have the space here. You see it clearly. That's A. Okay, so, and the B, yes, we can tell also from all the staples. Okay, that's this. And we may have questions. Okay, so how about the same problem? Boundary condition, the same boundary value problem. Now, how about if we try to use formulas with a smaller truncation error like this? Could we choose this? Yes, why not? You have the points x0, x1, x2. Okay, xm, m minus 1, 2. Okay. Now, the problems, this group of formulas, they both cannot be applied to which one? To this point, Therefore, we needed to derive formulas for this, to find formulas for the first, second derivative. Yes. And for this case, yes, as I said before, we needed to have formulas for the same with the same, which one? Truncation error in big O notations. Okay, now this one desperately backward will not work because you only have 1 point available. If you use this two for that one, the truncation error is big O of h. That's 2-point backward formula. It will not work. And therefore, only possibility is this, to develop or to find a forward formula, difference formula involving multiple points. Okay, with the truncation error, and I don't believe you can find it in your book and or in many other textbooks. Normally you cannot. Therefore, either you derive the formulas yourself, or try this. You can try that one as introduced in chapter 8. Okay, now this could help you easily find the formula. Okay, the same for this one. We cannot use forward one. The 2-point forward formula is with big O of h. That will not work. So this time we use backward formula. And as I said again, you cannot find such a formula in your book or in many books. You can use this to derive or to generate a formula. Okay, that's this. And one more example. Oh, okay. This time, oh my, the boundary conditions are different. They are not Dirichlet boundary conditions. They are the Newman boundary conditions. Instead of the functions y's value at the endpoints are given, now here is y prime. The first derivative at the two endpoints are given, and now we'll see how to apply such conditions. Okay, so this time we need to find a y at x0, y at 0, y at 5. All must be found, and other values plus. Yes, this time we need to discretize the problem at each point, every point here. Okay, it's not like with the Dirichlet boundary conditions, we discretize the equation only with the interior points. Now it's with all points. Okay, so we'll see, and say for at xi y sub I. Okay, given that we use these two formulas, the central formulas for y dot prime, y prime, as we did in last example. Okay, and we'll see, and they are not valid for the last point, right? For the last, they are not valid. So therefore, and this I must be 1, 2 until n minus 1. Okay, it's me. Now we'll see how to do it. And similar way, we'll replace this with this. That's y sub I minus 1, 2 yi plus 1 h squared plus 5 I plus 1 minus 1 2h and minus 6y sub I is 0. Oh, we don't like h squared, so we don't like it 2 also here. So each side multiplied by 2h squared, we will have a 2, 4, 2. Okay, and this we will have h. This we have, this will be, we will have 12h squared. Okay, so we will have 2y minus 1, 4y 2 plus 1, and by the way, You can find sample code for all examples except the previous one in Canvas. Okay, in the folder files, Canvas files, and then sample code. You can find the sample code for those algorithm examples in the very chapter. Okay. M plus 5hy plus 1 minus 5hy minus 1 minus 12h squared yi is 0. Combine like terms, we have 2 y minus 1 here, 2 minus 5h y minus 1 yi minus 4 this and this. Okay, 4 plus 12h squared, that's y sub I, and y plus 1, this 2 plus 2 plus 5h y sub I plus 1 is 0. Okay, I said I changed from 1 to 2. That's for all interior points. Okay, now how about we need to find y sub 0, y sub n, right? I did the two endpoints. So because they are not given, but the derivatives there at the point, the two endpoints are given. So we need to find the fourth derivative to find formulas, difference formulas for these two endpoints. As you can see, for this one you cannot go use back one, forward. We only have the choice to find a forward difference formula with the same truncation error, big O of h squared. Therefore, here you can find this and such a formula that's at I is 0. We will have, yes, this one. We apply which one? The boundary condition. Y prime at 0 is 0. Okay, therefore this equation is simplified. It's negative 3y sub 0 plus 4y1 minus y2 is 0. At I is m, the right endpoint was C. And this time we can only find which one? A backward formula. And we try to find it with such a truncation error. Therefore, here you go, we can have this. And we know at that point the condition is 1. Yes, the derivative at that end point is 1. So we simplify this guy, we get y sub m minus 2 minus 4y minus 1, 3y sub m is 2h. Yes, we now set up the system like that would be y0, y1, ym. Okay, have this. We have y sub 0, y sub m there. Okay, it's me. The fourth line is negative 3, 4, negative 1. Now, for all other points except the last one, okay, we'll see it's which thing. The equation will be this. So we put it here. When I, that's I is 1, you have a 2 minus 5h. Negative 4 plus 12h squared. And 2 plus 5h. Move to next line is 2 minus 5h. Negative 4 plus 12h squared. 2 plus 5h, and so on. All others, those are zeros. Okay, and you can do this. And finally, the last line here, if this last column is 3, and before it is negative 4, before it is 1. Yes, that's this. And how about B? A, Y is B. How about B? And as you can tell, it's which thing, as you can tell? Okay, let me erase this board. I'm sorry, we don't have much space here. B will be like what? B will be here as 0. That's B. B is equal to this. And the final one is 2h. And others, you'll see. How about others? Oh, how about others? Oh, they're all zeros. 0, 0. Oh, nice. You set up this and you solve it. Okay. Okay, that's this example. We just handled the Newman boundary condition. How about this time? It's mixed boundary conditions. At the left end point is Dirichlet boundary condition. On the right end, that's even not just simple. Which one? Newman condition. Because this way to solve is unknown. Okay. We'll see how to handle it. And this time only secondary two, so we choose this to do it. Okay, that's demonstration. Okay. And at this point, y0 is given, so we don't need to find it. Therefore, we discretize the system at those points. All points except the fourth one. Okay, we want to find the y1, y2, and the y sub m. Okay, we'll see how to apply the conditions. Okay, now replace y dot prime with this formula. With which formula? With this formula, 3-point central difference formula. That's 2 minus 1 h squared yi at I is which point? As you can tell, okay, at the xi, yi. We'll see later, we'll see i's range. And plus 0 to xi sub I is 0. Well, I changes, as you can tell, this formula is not valid. Though we care about this, it's not valid for this point, right? Therefore, I is 1, 2 until n minus 1. Okay. And simplify it. We don't like h squared. Each side multiplied by h squared. We have h squared. Okay. Combine like terms. Let's see. yi minus 1, we have 2 yi minus 1. I plus 1. Yi, we have negative 4 yi and minus h squared, right? That's minus. Is this negative 4 yi and yi. Okay, it's this. So it's 4 plus h squared yi. And now yi plus 1. Only that it's just 4 y sub I plus 1. Okay. And then move this to the other side. It's negative h squared e negative 0 2x sub I. Okay, I changed from 1 to until n minus 1. Okay, also we need to discretize at the last point. Okay, at this I is m, and we want to find a formula to apply this condition. We need the first derivative, right? A formula for the first derivative. We only, as I said, we can only use a formula, a backward formula with such truncation error. Now you can use this one. Okay, and this one, okay, we multiply each side to h as y n minus 2, 4y n minus 1, 3y sub m is negative 2h y sub m. Okay, so, and yes, that we apply the condition here. Okay, oh no. And this we need to do what? For this we need to rewrite it to combine like terms. So this, we move this to the other side as a 3 plus 2h. 3 plus 2h y sub m is 0. Yes. And this, if we expand this, we'll get a system y, ay is b. It's like this. Okay. And y is y1, not y0, y2, ym, right? We have this. And when I is 1, you set up this. That's 4, that's 2, negative 4 plus h squared, and 4. Second, when I is 2, you have which thing? Okay. Oh, here. When I is 0, there, sorry. When we have the left end point, the condition we haven't used. When I is 1, we can apply the condition. What's this guy? Y, that's 2, y sub 0, that's just 2. We move to the other side. That's negative 4 plus h squared, 4. Okay, that b, as you can see, b will be what? B, we do need, space is a problem. Okay, you move that to the other side. That's b, the b1, b sub 1. Okay, now the second equation is 2 negative 4 plus h squared, 4, and 2 negative 4 plus h squared, 4, and so on. Okay, and so on. And the last equation will be this, given that that's the last column, you have 3 plus 2h. The previous one, negative 4, the previous one's 1. Yes. Okay, so, and as you can tell, normally when we arrive at such a linear system, it's always spatial. You have, if you use more points, this should be a sparse matrix. Non-zero, all non-zero, in our case, all non-zero atoms are located at which one? The main diagonal, and the diagonal right above the main diagonal, the diagonal right below the main diagonal. All others are zeros, so they're special. That's why in chapter 4 we studied how to solve which one? A tridiagonal system, right? Yes. Actually, it depends on your formulas. Sometimes the non-zero vectors could be located here. Okay, that's and more, but most are just zeros. It depends. Okay, on which formulas you use and the equation. Normally, it's the formulas we use. Okay. Anyway, yes. Today we have, in summary, we have studied how to discretize which one. ODE, boundary value problem. Yes, applying the finite difference methods. We have seen some examples. Okay, I hope after the class you will find the sample code in Canvas and then play with them. Okay, good. Thank you for watching.